Okay, so today we are starting lecture number 4. So last time we did some basics about the confidence interval. Now today we'll build on that and we'll study some more regarding the confidence interval. Okay, so let me switch my camera. So today it's lecture 4. Now, before starting anything, let me show you one thing that I forgot to mention last time. So here is an aside from last time. So last time we studied some critical values of Z. For instance, suppose this is the Z distribution. And we call, so suppose this region is alpha over 2. Then the value of this one is Z of alpha over 2. Okay, which appeared in my previous lecture. Okay. So in the language of something that we remember that phi of Z is probability that big Z is less than little z. Okay, so big Z is really the normal distribution, which means zero variance. One is the standard normal distribution, right? So that's a notation that we frequently used in the last course. So this is the definition. So this is the little z and this is the big random variable Z. Okay, so what's the relation? So therefore the relation is if I want to see, I mean this area, so phi of say Z of alpha over 2 is probability that Z is less than this point. So that is basically 1 minus alpha over 2, isn't it? Because you just subtracted this alpha over 2 from 1. Okay, so that's how we can compute it. For instance, here is an example from the last class. In the last class, we wanted to find, say, let's see, there was one point where we wanted to find Z of, suppose we wanted to find Z of 0.05. So that means what we are really trying to find is Z of, so phi of 0.05 would be equal to 1 minus 0.05, which is 0.95, right? So we are asking for a value. So we are asking for something. Maybe it's here, Z of 0.05. So that this area here is 0.5 and the area to the left is 0.95. Okay. Now, there are many ways of finding this from the table. Again, so for those who took the course with me last semester or took any course last any previous course, you know that there is a Z table, but also you can, let me just stop sharing for a bit. Let me share one screen. So there is one way of computing this, just like as I showed you last time. There was a table. And again, you don't have to use this table. There are plenty of other tables available in the market. So for instance, you can use, I can just basically do a Google search and find any table you like. Okay, but here is the one that I found. So it's calculator.org. I'll again post it on Brightspace. If you go to this alpha value, so this is what you really need to do is basically you have to write the value of, so in our case, whatever the area to the right side. Okay, so because you'll see that this alpha is not our alpha over 2 that I wrote. Okay, so if you look at that, so it's basically so the probability of the alpha value. So in this case, I'll write say 0.05. That is our alpha. And then it will be spitting out a number, which is right here. Okay. So So this is one way of computing the z value. Okay. So in the last case, we found that so this is giving me. So let me stop share. So this number here we found is so z of 0.05 is what we just have seen. It's 1.645. Okay. All right. This is just an aside. You can use again. Please feel free to use the tables for computing this. So that's also perfectly fine. But if you happen to use any link, so that is how you can do it. All right. Now, so what we did last time is we'll build a so very briefly speaking. So again, back to the main topic. So we have built two confidence intervals. So last time we computed this as 1 minus alpha is probability of the t statistic. So it's alpha over 2 n minus 1 less than t alpha over 2 n minus 1. So that's one way. This is for any distribution. And then we sorry, this is for the case when we assume that the original distribution. So this is for the case when we assume that, say, x1, x2, xn are a random sample from the normal distribution. Right? And then what we found is the confidence interval. So in this case, we found that the confidence interval for mu, we found the confidence interval for mu is given by, we have done everything last time, so let me just write it this way. The confidence interval, and by that I mean 1 minus alpha 100% confidence interval for mu is given by x bar from the sample minus t alpha over 2 n minus 1 s over square root of n to x bar plus t alpha over 2 n minus 1 s over square root of n. Okay. That's what we found. Now, what happens for the case when the samples are not drawn from the normal distribution? So we have also seen that in that case, this is, let me just write as number 1. I'll refer it later today. And number 2 is, so suppose that we have any observations again. So we found that 1 minus alpha. So if x1, x2, xn is a random sample on a random variable x with mean, mu, and variance sigma squared. But the distribution, so I mean, this x not necessarily normal distribution, normal. In that case, we found that the confidence intervals, so then the confidence interval, 1 minus alpha 100% confidence interval for mu, is given by approximately, so this is always an approximate, It's x bar minus z of alpha over 2, and this is the z that I showed you at the beginning of the class today, s over square root of n, sorry, so 2 x bar plus z of alpha over 2 s over square root of n. Okay, this is my number 2. So this the main difference is this is an approximate version, and the previous one is the exact version. Okay. Now, please note that this approximation can be exact based on certain things. For example, if the original x is normal, then it's actually exact. Okay, we'll do an example. We'll see. Okay. All right. Now, let's see. So what we'll study today is the so-called the confidence interval for the difference of mean. Okay. Okay. So what is the like underlying problem? So the problem here is to compare, the goal is to compare two distributions. Okay. So we are comparing two distributions of two random variables, x and y. Previously, we had just one distribution, and we are trying to find its mean, right? And we are trying to have a confidence interval of its mean. But now, suppose we have like we have two distributions, x and y, and we are uh, trying to have some idea about how these two distributions can be compared. So suppose the expected value of x is mu1 and expected value of y is mu2. These are the population mean, meaning that this is the exact mean. So the idea for the original distributions, the means for the first one is mu1 and the means for the second one is mu2. Also, let's define the variance of x to be sigma 1 squared and variance of y to be sigma 2 squared. Once again, these are the population variance. Okay. So far, we didn't draw any sample. Okay, so the goal is to compare two distributions which has originally given like that. Okay. But the problem is now, if you know these numbers, you actually know everything. But the problem is in real life, we only draw a sample and we conclude based on that. So let's draw a sample. So let x1, x2, xn be a random sample from x and maybe y1, y2, yn is a random sample from y. Okay. And we assume that so the samples are gathered independent, like x and y samples are gathered independently. Okay, so we assume that samples are taken independently. So x samples and y samples are taken independently. Okay, now based on this sample, I can compute a sample mean. And based on this sample, I can compute a sample mean for, so this will be the sample mean for x and this will be the sample mean for y, right? So let's compute those. So my sample mean so the sample mean for x is given by x bar, which we all know. So suppose there are, okay, so let's make this little different. So suppose we have maybe n1 samples for x. Let's make it n1 just to have two different numbers. Okay, and maybe n2 samples for y. Okay. This n1 and n2 may or may not be same. So then the sample mean for the x would be 1 over n1 summation I from 1 to n1 xi, right? And the sample mean for y is given by y bar equals 1 over n2. There are n2 numbers of samples, I from 1 to n2 y sub I. Right? Now, we have no control, or we cannot see this mu1 and mu2 directly. That's a problem. So we can estimate this mu1 by x bar, and we can estimate this mu2 by y bar. Now, when we are trying to compare the difference between mu1 and mu2, if you can see it, you know the number, but since we cannot see it, so every time you draw a sample of n1 size n1 for x1 and you compute the sample mean, it will be a number, and for y it will be another number. You take the difference. Okay, so that will be a number, right? So what we really want is we want let's call the difference in sample mean is x bar minus y bar, right? Let's call this by a letter, say delta hat. Okay. And what is my delta? So with delta is the mu1 minus mu2. So this is for this is the exact one. So this is for the population. And this is for the sample. And by the way, we have already proved that this x bar is an unbiased estimator of mu1. So that means E of x bar is mu1, E of y bar is mu2, and hence we have E of delta hat is delta. So delta hat is an unbiased estimator for delta. Okay, this is just an aside. Okay. Now, remember that by the central limit theorem, we must have, so if we can construct, say, I mean, we have no control over the distribution, but what we know is the following. So by central limit theorem, we know that for large n1 and n2, so this quantity, delta hat minus E of delta hat over square root of variance of delta hat, this is approximately normal, right? It approximately follows the standard normal distribution. For large n1 and n2. So that means when the samples are drawn large, I mean, there are a large number of samples, then this is approximately normal, right? Now let's compute. So we have already computed E of delta hat, so which is right here. So this is delta. So it's basically delta hat minus delta over variance of delta hat. So what is variance of delta hat? Well, so I can compute variance of delta hat here. So it's basically variance of x bar plus variance of y bar. And plus there is a covariance term between x bar and y bar, but we can drop it because of the last sentence that the samples are drawn independently, right? So there is no other term, and that's pretty much it. And variance of x bar, so that's the variance of x bar, we have done it some time back. It's sigma 1 squared over n1. Okay. What was sigma 1 square? Remember that sigma 1 square is a variance of x, so it's sigma 1 square over n1, and this is sigma 2 squared over n2. Please don't get I'm going to get this confused, because I'm not talking about the sample variance here. I'm talking about the variance of x bar. Sample variance for this case is we typically wrote it as s squared, right? So there is a sample variance which is different. I mean, this is the variance of x bar that we are talking about here. All right. So now I can just plug it here. So I can say that this quantity approximately follows. I'll just copy it here. Sigma 1 squared over n1 plus sigma 2 squared over n2 is z. Okay. And now we don't have much work. So we have already established the fact that in the case of this, which is my case 2 that I wrote on my second page today. So we have an estimate of the confidence interval. Okay, so basically, if I want to have the confidence interval for the difference of the mean, so therefore um, the confidence interval 100% approximate. Why approximate? Because remember that for this case, for the case 2, we write approximate because we have no original, like we don't know how the original distributions are. So they are not necessarily normal, right? So here we don't assume anything about normality. So it's basically approximate. So we write, so the 1 minus alpha 100% approximate confidence interval. Let me just write approximate after the confidence interval. Otherwise, it looks like this is approximate. So confidence interval, which is approximate for what? So this is for the difference of the means, right? So remember for the previous case when we considered this one, it was the confidence interval for mu, right? And in this case, mu is replaced by the difference of mu. So it's the confidence interval for mu1 minus mu2. For mu1 minus mu2 is, how do I compute it? So it's basically the observed. Let me just write this one. So this is, remember that the previous case it was x bar. What was x bar? So in our case it's the x bar for delta hat. So delta hat is the difference between two samples, right? So I can simply write. So remember that this delta hat is nothing but the difference of two samples, right? So it's basically I can write this as x hat minus y hat minus, now note this one here, this is z of alpha over 2 and then s over square root of n, right? Now here this s over square root of n was due to the fact that we estimated this from the sample. So we had a sample variance and then we computed this one, right? So if you recall, so the way we found it, but here we have this, I mean, this is, let me just show you from the last class. So where did that come from? So if you recall the last lecture, so here, there was a Zn, which was x bar minus mu over s over square root of n. And that s over square root of n is reflected here, right? In our case, what we have is we have this quantity. So if you compare that Zn with what we have here, so this x bar is like delta hat, this mu is like delta, and then this quantity is like this one, right? So this is the whole thing. So my whenever you see that s over square root of n, that is replaced by what we have here. So let's write it down. So we have z of alpha over 2 and then the whole thing. So it's basically we have s1 squared over n1 plus s2 squared over n2. By the way, what is this s1 and s2? This is the estimator for sigma 1 squared. So it's a sample variance for sigma for x1. So S1 squared is the sample variance for x x2 xn1. And what is S2 squared? So S2 squared is the sample variance for y1, y2, yn2. Okay. So that's the first one. And where does it go up to? So basically I wrote this one. So the other one will be just the same thing with plus sign. So it's going to be x bar minus y bar plus z of alpha over 2. And then this one, S1 squared over n1 plus S2 squared over n2. That's it. So this is the confidence interval. Okay. All right. Two things. One is I wrote this is an approximate confidence interval and 1 minus alpha 100%. And this is the interval we are talking about. So that means mu1 minus mu2 is bigger than this one and less than this one for a given sample. Let's see, I mean, if we can understand this a little better with some examples. So now this approximation, when can it become say maybe the exact? So we can try checking that. So let's do an example problem here. So I'm talking about, so this is exercise 4.2.23. Okay, so which goes like this. So it is asking, so discuss the problem of finding a confidence interval for the difference mu1 minus mu2 between two means of two normal distributions. If the variances sigma 1 squared and sigma 2 squared are known but not necessarily equal. Okay. All right, so what is the problem here? So the problem here is we are trying to see what happens for the case when we are trying to find the confidence interval of the difference of the means for the two normal distributions. So what is so special about this one? Remember when we studied the previous problem, by that I mean the one that I just wrote here. Here we didn't assume anything about the distribution. Okay, so here we write this mu1, we write this sigma 1 square, but they are not necessarily from a normal distribution, right? And that's why, since they are not necessarily, so this I mean x bar and y bar, let's write this way, x and y are not necessarily normal. That was the underlying assumption. And that's why when we computed the confidence interval, it was approximate, right? Now let's, for this problem, for problem number 23, it's asking what happens if the confidence interval is actually, what happens if the original distribution is actually normal. Okay. Also, it's given that this the sigma 1 squared is known and sigma 2 squared is known. So I don't have to write S1 squared. I can simply replace this by sigma 1 squared and this by sigma 2 squared because it's known. So when we don't know that sigma 1 squared and sigma 2 squared, so that's when we have to compute S1 squared and S2 squared. But if they're known, you don't need to compute those, right? So you can simply use whatever value is given, right? So let's solve this one. And this is and also in this case it will be not be approximate. So when we are talking about the normal distribution, so if the original distribution is normal, so this will not be an approximate. This is an exact equal. Okay. So what we have is the following. So solution. So 1 minus. So we're trying to find the confidence interval. So what will happen is uh, when the distributions are normal, we must have 1 minus alpha is equal to, this is equal, okay? So note this. It's not approximately equal. It's equal to basically x bar minus y bar minus mu1 minus mu2 over sigma 1 squared over n1 plus sigma 2 squared over n2. This is now standard normal, right? So x bar minus y bar is my so if x and y are normal, so then x bar minus y bar is also normal, and then I subtracted its mean. I divide by the square root of the variance, and the quantity that I'm needing is basically it's less than z of alpha over 2 minus z of alpha over 2, right? By the way, if you don't like it, another way to write it is exactly what I had before. It's basically this interval. So let me just write it. So this is really probability of, if I simplify this for mu1 minus mu2, so simply so solve it for mu1 minus mu2. So I have to multiply with this one. So it's minus z of alpha over 2 square root of sigma 1 squared n1 plus sigma 2 squared over n2 less than x bar minus y bar minus mu1 minus mu2 less than z of alpha over 2 square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And then if I solve for mu1 minus mu2, I get x bar minus y bar minus z of alpha over 2 square root of sigma 1 squared over n1 plus sigma 2 squared over n2 is less than mu1 minus mu2 less than x bar minus y bar plus z of alpha over 2 sigma 1 squared over n1 plus sigma 2 squared over n2. That's it. So this is the confidence interval. Okay, so that is how you compute the confidence interval, and this is exact. Previous case, it was approximate, because if you don't know anything about the distribution, if you happen to know the distribution, this is 1 minus alpha, and that is the answer. Okay. The confidence interval, the 1 minus alpha percent confidence interval is given by this one. So this is the 1 minus alpha 100% confidence interval. By the way, what is the interval? So if you want to write the interval one, it's basically here to here. I'll not write it. Okay, now we have done many examples, so you know this. Okay, let's do one more. Let's do another problem so that we understand this better. So this problem is 4.26. The next one. So example 4.26. 4.2.26, sorry. Okay, it goes like this. So it goes like this. Let x bar and y bar be the means of two independent random samples, each of size n. Okay, so in the last case, remember that we had some n1 and n2, but here we are assuming that each of this x bar and y bar are taken from a sample of size n, the common size. Okay. From the respective distributions n of mu1 sigma 1 squared and n of mu2 sigma 2 squared, where, sorry, let's write this same variance, sigma 1. So they have the same variance, okay, where the common variance, remember, these are usually for the population, so we don't know it, but suppose for some reason we know this one, for this one, where the common variance is known. Okay. Find n such that probability of x bar minus y bar minus sigma over 5 is less than mu1 minus mu2 is less than x bar minus y bar plus sigma over 5 is equal to 0.90. Okay. So that is the problem. So this problem is asking you to find confidence interval or find the value of n. Find n. What is the sample size? Both of the samples are of size n. So what is that size? So that I mean, if you know the sigma, where I mean, the difference between the means are falling within this range, which is x bar minus y bar minus sigma over 5 to sigma x bar minus y bar plus sigma over 5. So the difference is given by, so the probability of this is given by, it has 90% chance. All right, so here's the solution. So basically you start with 0.90 and you write this one. So you have, it's given by probability of x bar. I'm just rewriting it, okay? So you don't have to do it, but let me just show it. Mu2 less than x bar, sorry, minus y bar plus sigma over 5. That's what is given. Okay, there is nothing special here. Let's solve for, I mean, I want to see this in the form of this one, something like this one. And then I can do something, okay? Now, remember that both are drawn from the normal distribution, so this equation is exact. So this is exact equality as the distributions are normal. Remember that it's not really exact if the distributions are not normal, it's approximately equal. But here, I'm talking about the exact equality. All right, so let's write this as probability of, if I write minus sigma over 5 less than, so I can write this as x bar minus y bar minus mu1 minus mu2 is less than sigma over 5, right? You can easily check it. So basically what I'm doing is, in order to do it, what we do is basically look at the left inequality. So it's x bar minus y bar. And if I move this mu1 minus mu2 here, so it will be x bar minus mu1, y bar minus mu1 minus mu2 is less than sigma over 5. That's this part. And if you look at the right side, so if we have this x bar minus y bar, and if I move this here, so it will be minus mu1 minus mu2, it will be bigger than minus sigma over 5. That's the left side. So after some tweaking, you can get that. And that means we have the following. So we have probability of, let's see. So now, what is the quantity that we need in the denominator? So if you look at the last example, we know this one, right? So for the random samples, for the normal samples. So in our case, N1 and N2 are same, sigma 1 squared and sigma 2 squared same. So that means we have this quantity, sigma 1 squared over N1 plus sigma 2 squared over N2. In our case, sigma 1 equals to sigma 2 and N1 equals to N2. So this is going to be equal to, so what is that? So it's basically square root of uh, 2 sigma squared over N squared. So this is equal to sigma and this is equal to N, right? So what we have is really, it's square root of 2 sigma over N. Right? Let's divide by that because I'm trying to match it with this one. So I already have set up this x1 minus x2, mu1 minus mu2. So let's divide by this quantity, which we found out to be what I just said. It's sigma square root of 2 over N. So I have x bar minus y bar minus mu1 minus mu2 over sigma, sorry, there is no N squared. So it's basically N1 and N2. So it's replaced by N and it's replaced by N. So it's basically N. So I should have a square root of 2 over N here. So it's sigma square root of 2 over N. I divided by that. So I have to do that same thing for the other sides. It becomes the square root of N goes to the top and sigma divided sigma goes away. So it's 5 square root of 2. And here it becomes minus square root of N, 5 square root of 2. Okay. So far, so good. Now, you know that if that is the case, what you really have is, remember, so this equation, so that is always true. Now, if that is the case, so 1 minus alpha equals to this one, whatever you have here, it's z of alpha over 2. So in this case, this quantity got to be z of alpha over 2. And what is alpha? So again, this is equal to 0.90, which is 1 minus 0.1, right? So my alpha is 0.1. Okay, so we must have the square root of N over 5 square root of 2 is z of alpha over 2. So alpha over 2 is 0.05. So 0.05. 0.05 is something I've shown how to compute at the very beginning of the class, which we found to be 1.645. You can use your table, or you can use any online sources that I mentioned. Okay. So I have a nice equation. I have this equals to this. So if I compute the n from here, so n is equal to basically 5 square root of 2, and then 1.645, and then squared. So n is approximately equal to 135.30. So so the question was find n such that this is true. So n would be equal to the nearest integer would be 136. By nearest integer, I mean, don't make it lesser than 135. Then what will happen? This probability will be less than 0.90. Make it more so that it's a little bit more than that. But so that is the exact number of n that we need. Okay, because n is a number of samples. So samples cannot be fraction, and that is the answer. Okay, so this is how things are done for the samples for the difference of two means. Okay. So now let's talk a little bit more about something else. So we are still on the difference of the means, but these are just the two stray examples, which is necessary at this point. But now let's talk about, let's go back to the original topic. We have done some special cases, but by special cases, I mean the cases when X is normal, but X and Y are normal, but still, like in general, it's always the approximate. In general, whenever we don't know anything about the distribution, so this interval is approximate. How to make it concrete? Okay, so in order to make it so back to the approximate confidence interval when X and Y are not necessarily normal. Okay. It can be shown, and I'll skip this part. So it can be shown that in that case, the quantity T, which is given by X bar minus Y bar minus mu1 minus mu2 over SP square 1 over square root of n1, 1 over n1 plus n2, where SP is a sort of weighted average of the two sample variances of X and Y. It's given by n1 minus n1 s1 squared plus n2 minus 1 s2 squared over n1 plus n2 minus 2. It has a name. It's called the pooled estimator. Okay. It's called the pooled estimator of sigma squared. So what we are assuming is so here we are assuming that both of these quantities we are assuming not necessarily normal. Assume that the variance of X is equal to variance of Y equals sigma squared. That's an assumption which is used here. Okay. And that sigma squared can be captured. The estimator for sigma squared is this. Okay. All right. So we are now in the situation where the variances are the same and the distributions are not necessarily normal. So it can be any distribution where the variances are the same. And then it can be shown that then what I wrote here, T, this, it follows, this T follows T distribution with n minus 1 degrees of freedom. Plus n2, well, n1 plus n2 minus 2 degrees of freedom. Okay. And in this case, we can show that, so I'll not show, which is very similar to what we did before. In this case, so that is the first remark. And the second remark is, in this case, and also I don't want to write this n1 plus n2 minus 2 all the time. So let's write this n1 plus n2 as the total number of samples, which is n. Okay. So in this case, the 1 minus alpha 100% confidence interval for the value of delta, which is the difference between two means. So what is the difference between this and the previous example? So previous one was the approximate. Now we want to find the exact. Okay. So this is given by the following. It's X bar minus Y bar T of alpha over 2 comma n minus 2. By the way, n is again n1 plus n2. Okay. And then we write here SP square root of 1 over n1 plus 1 over n2. 2. The other one is the same thing with plus sign. So it's X bar minus Y bar plus T of alpha over 2 comma n minus 2. So this is a T statistic with alpha over 2 and n minus 2. And then write SP square root of 1 over n1 plus 1 over n2. So n is again n1 plus n2. This expression. Okay. All right. So that is the and this is not an approximation. That's the upgradation over the previous discussion. Okay, so the previous discussion gave us actually an approximate expression, but this one is actually giving us an expression which is which is not really approximate. Okay, so at this point, let's solve a problem based on this. So let's do. Let me get some more papers. So let's solve. Let's see. I'll do number 21. So it's exercise. So this is 4.2.21 to see how it works. It goes like this. Let two independent random samples each of size 10 from two normal distributions n1. So the n of mu1 sigma squared and n of mu2 sigma squared yield x bar equals to 4.8. So suppose we drew samples of size 10 from two normal distributions, and I found that x bar, so for those 10 samples, x bar is the sample average is 4.8. Sample mean is that. S1 squared, that's the sample variance, is 8.64. Y bar is 5.6. And S2 squared, for Y, the sample mean is 5.6. For Y, the sample variance is 7.88. The goal is find a 95% confidence interval for mu1 minus mu2. Okay. Okay, so let's and we'll do it with using a T statistic, the one that we just learned. So let's see how to solve it. All right, solution. Now, first of all, observe that we have the variances sigma squared and sigma squared. They're equal, so the variances are, so population variances are equal but unknown. We don't have any information about sigma squared. So what we can do, we can use like the pooled variance as an estimator of sigma squared. Okay, what is pooled variance? That's the thing that I wrote right here. Okay. So pooled variant, so it's an estimator for sigma squared. I didn't prove this one, but it's very easy to prove. So I'll be using pooled variance. Okay, so let's compute the we use pooled estimator of sigma squared, which is given by sp squared, which is equal to n1 minus 1 s1 squared plus n2 minus 1 s2 squared over n1 plus n2 minus 2. For our case, n1 is 10, n2 is 10. So it's 18. And these numbers are, everything is, sorry, this is n1 and this is n2, yeah. So this is going to be, if you compute this, it's basically this n minus 1 is 9. So it's 9 times s1 squared plus s2 squared, which is 8.64 plus 7.88 over 18, right? So which is 8.26, which implies SP. So SP is the square root of this one, which is 2.874. Okay. So thus, so we are trying to find a 95% confidence interval. So thus a 95% confidence interval. Okay. By the way, just to remind you, so that means 1 minus alpha is given by 0.95, right? That's a 95% confidence rate. So alpha is 0.05. Remember, for the we already wrote it. So here we need some alpha over 2, right, for the confidence interval. So what is alpha over 2? So alpha over 2 is 0.025. Is given by x bar minus y bar plus, sorry, minus t of alpha over 2, which I found to be 0.025, and then n minus 2. And n is basically n1 plus n2 is 10 plus 10, 20 minus 2, which is 18. And then I have sp square root of 1 over n1 plus 1 over n2. I'm just using the formula that I wrote before, this one. 2, the same thing, x bar minus y bar, and then the plus sign. T of 0.025, 18, sp 1 over n1 plus 1 over n2. Okay, plug in all the numbers. So it's basically x bar minus y bar is 4.8 minus 5.6. So it's minus 0.8 minus, I'll not show it again, but we have already known how to compute this. So this number is a test, so the t value. So this, if you can check that this is going to be 2.10. So it's 2.10. SP, we found it's 8.26. And then this quantity is basically 1 over 10 plus 1 over 10. So that's one square root of 1 over 5. That's it. 2, the same thing with the plus sign. So it's minus 0.8 plus 2.10, 8.26 square root of 1 over 5. And if I simplify this expression, this is minus 3.50 through 1.90. That is the answer. Based on the sample, this is the confidence interval. Okay. All right. So we understand how to compute the exact value of the confidence interval based on certain samples. Okay. One last topic on this one. So this is what we started here is the sample values for the difference of the means. And now we can do something which is called this, sorry, what we have done just now, it's called the confidence interval for the difference of means. Now, what about we do something called confidence interval for the difference of proportions. I'll explain what it means, but let's do it. Okay. For this, let's okay. So let's write this first. So it's a confidence interval for difference in proportion. Okay, the last one was the mean, and this one would be for proportion, which is very similar though. Okay. Now, before doing that, so let's quickly cover one thing that we didn't really do it for last time. So this is called the large sample confidence interval. Interval for P. Okay. So this goes like this. Suppose we have let X be a Bernoulli random variable. What was a Bernoulli random variable? So it's a random variable that can either take the value 1 or 0, 1 with certain probabilities, 0, 0 is 1 minus that probability, right? So let's let X be a Bernoulli random variable with the probability of success equals P. Okay. So basically what I'm assuming is X equals to 1 with probability P, 1 is my success, and 0, which is failure, with probability 1 minus P. Okay, so that's a very simple Bernoulli distribution. Okay, now suppose that we have a bunch of samples drawn from this Bernoulli distribution. So say x1, x2, xn is a random sample drawn from this Bernoulli distribution. Random sample from the distribution x. Okay. Now, I think I've shown that there is an estimator. I think we have shown it in one of the previous classes. That suppose we count the number of successes in this sample and divide by the total number of the sample, which is n. So number of successes or number of ones in the n sample over n. That is the proportion of success in the sample, right? So p hat is the sample proportion of success, which is given by literally the number of ones in the sample over n. Okay, so that is called the sample proportion. Another way of writing this, remember, these numbers can be either 1 or 0. So if it's 1, then only it's meaningful. So it's basically I from 1 to n xi. Remember that whenever I is 1, then it's picking up a number. Otherwise, it's 0 over n. So that's my p hat, right? So p hat, which is basically the sample proportion of success. It's also called the sample average. Okay. Also, what is the variance? So basically now I can compute the variance from this expression. For those who forgot, so if we have so x1, x2, etc., they are following a Bernoulli distribution, right? With probability of success p. What is the value of e of x I for every I? Well, it's got to be p. And what is the variance of xi? It is p times 1 minus p. We have done this in one of the, you should have seen it in one of the previous courses. So this is for I equals to 1 to n for every I. Okay. Now, what we are doing is basically, let's compute the when we have a sample, let's compute the variance. Okay. So let's compute the variance of p hat from these expressions. And by the way, these are independents because it's a sample. So it's basically the sum of the variance of xi over n squared, right? And then there are how many variances are there? All these variances are p times 1 minus p over n squared. So there are n of those. So it's n times p 1 minus p over n squared. So it's basically p 1 minus p over n. So that is the variance of p hat. What is the expectation of p hat? So expectation of p hat would be summation I from 1 to n e of xi over n. And each of this e of xi, as I said, it's basically p. So it's summation I from 1 to n p over n. So it's really n times p over n. So expectation of p hat is p. And that's why this p hat is an unbiased estimator of p. We have done this before, but I'm just doing it again. I mean, to show that p hat is also an unbiased estimator. Okay, so far so good. So if you have n samples, so that's what the mean and variance. Okay, now referring to the previous discussion. So therefore, by the central limit theorem, the expression which is given by p hat minus e of p hat over square root of variance of p hat is approximately normal, standard normal, right? For large n. Okay. In other words, so we can define this quantity. We have already computed this. So that means p hat minus e of p hat, we found p, and then the square root of variance of p hat is basically, we found this to be square root of p 1 minus p over n. Okay, so this is approximately standard normal for large n. Okay, now as we have done before, so hence an approximate 1 minus alpha 100% confidence interval for p is given by, I'll leave it as an exercise. So this is given by p hat minus z of alpha over 2. Remember, I'm approximating with z. So see, the original distributions are not normal. They are approximately normal. So this is an approximate confidence interval. And then basically this is square root of p hat 1 minus p hat over n. 2, this plus sign, p hat plus z of alpha over 2, square root of p hat 1 minus p hat over n. This is basically coming from this expression. The only thing is, since we don't know p, we are trying to find the confidence interval. We are trying to estimate the variance based on what we know. So that's why these numbers are p hat. Okay. So here, this quantity, this, since we are mentioning it, so this p hat 1 minus p hat over n is called the standard error of p hat. Okay. All right. So this is an approximate confidence interval for the case of proportion. So when you cannot see, well, when the each of this this sample is following a Bernoulli, and you are seeing the proportion, that's how you check. Okay. Now back to the topic that we started discussing. So how do we really compute the difference? So back to, so this is for the one proportion. Okay, so back to confidence interval for difference in proportion. Okay, and this will have a tremendous application. You'll see. Okay. So suppose x and y are two independent random variables. X follows Bernoulli with parameter p1, and y follows Bernoulli with p2. And x and y are independent. Okay, so goal is to find a confidence interval for p1 minus p2. Okay. Again, we'll not go over the procedure. The procedure is very simple. It's basically the same thing that we have done for the many previous problems. So let x1, x2 up to xn1 is a random sample for x, y1, y2, it's actually random sample from x, the distribution x, y1, y2 up to y sub n2, it's a random sample from y. Okay, and they are collected independently of one another, meaning that my x and y are independent and all the samples are independent. Okay, let as before n equals to n1 plus n2 is the total sample size as before. Okay, we want to estimate the difference between p1 minus p2. Okay, in this case it can be shown that again, so in this case it can be shown that the approximate 1 minus alpha 100% confidence interval for okay, before doing that, sorry about that. So I forgot to define some terms. So let's define those. So because I have to write those. Okay. Now, what is this? So I'm trying to find the goal is, once again, goal is to find a confidence interval for P1 minus P2, right? Now, P1 and P2 are unknown. So they are from the for the population, right? So what we can do is we can try to find those numbers for the samples, right? Now, for the sample, x1, x2, all the way up to xn1, we compute x bar, sample mean. And now it's for the case of the proportion, when we compute the proportion, in this case, its traditional notation is P1 hat. It's a notation. It's basically same as X bar. There's no difference. It's really X bar. But the notation we use is P1 hat. It's an estimator of P1 because E of X bar, remember, it's actually, so we have computed this right here. So we have seen that. So where did we compute it? It's right here. So P hat is given by really P hat is the sample proportion, which is really, this quantity is really X bar, isn't it? This is the definition of X bar. Okay. So when we compute the X bar, we call it P1 hat. And similarly, for the sample Y1, Y2, Yn2, compute Y bar, and let's call it P2 bar, P2 hat. It's again a notation. Okay. So then, therefore, for this, like for the first sample, it's P1 hat. For the second sample, it's P2 hat, and also here the variance can be approximated. So for this case, also I can write sigma 1 squared is 1 minus, sorry, P1 times P1 minus P1. So that means in this case, this can be estimated by P1 hat, 1 minus P1 hat. And also in this case, same thing. So also sigma 2 squared is P2, 1 minus P2. And this can be estimated by all the hats. So estimated by P1 hat, 1 minus P1 hat. And here, the same thing, estimated by P2 hat, 1 minus P2 hat. And with this, we are ready to write the final result. The final result is right here. So what we wrote here. So this is the confidence interval. So approximate here. Hence, the approximate 1 minus alpha 100% confidence interval for P1 minus P2 is basically P1 hat minus P2 hat. I'm just copying what we have here. Okay. Except now we have a sample of size 2n, right? N1 plus N2. So P1 minus P2 hat minus Z of alpha over 2 square root of, now previously we had just one variance, now we have two. So it's basically P1 hat, 1 minus P1 hat over N1 plus P2 hat, 1 minus P2 hat over N2 through the plus sign, P1 hat minus P2 hat plus Z of alpha over 2, P1 hat, 1 minus P1 hat over N1 plus P2 hat, 1 minus P2 hat over N2. That's it. This is the interval we are talking about. Okay. Now, let's do an example as we have done for all the previous problems. So I'll solve 4.2.22. So this is the example. 4.2.22. It goes like this. let two independent random variables y1 and y2 with binomial distributions have parameters n1 equals to n2 equals to 100 and p1 and p2 respectively be observed to be equal to y1 equals 50 and y2 equals 40. Okay. So we have two independent random variables, y1 and y2. Both of those follow binomial distributions. With parameters for y1, it has 100 comma p1. That's the parameter. And for y2, it's 100 comma p2. In other words, I can think this y1 as it has a Bernoulli distribution with proportion p1, and we have a sample size of 100. And I can think of y2 as a Bernoulli distribution with the parameter p2, and we have 100 sample of that. Okay, so that's another way of thinking. Okay, now here, determine an approximate. By the way, we see the value y1 to be 50 and y2 to be 40. Okay. So determine the approximate 90% confidence interval for P1 minus P2. Okay. So it's basically an problem based on the just by the quantities that are given. All right. So solution. So what is the estimator P1 hat? Well, so there are, so Y1 value is 50 and there are trials 100. So it's 50 over 100, that is 0.5, right? What is an estimator for P2? So there are 40 over 100, so it's 0.4. So these are the estimators for the success, so the proportion of success, right? So therefore, I'll simply use this one with the fact that what is my z of alpha over 2? We have done this exercise enough. So it's a 90%. So I have 1 minus alpha is 0.9. So alpha is 0.1, right? So that means alpha over 2 is 0.05. So that is my alpha over 2. So the required confidence interval is, if I just copy it from here, so it's basically P1 hat minus P2 hat, which is 0.4, 0.5 minus 0.4, which is 0.1, minus Z of 0.05. And then this quantity is you have to compute. So it's based on P1 and P2. I have this number. So by the way, here N1 equals to N2, both are 100. Okay. So this number is actually, if you compute it, it's 0.7 over 10. Okay. Through 0.1 plus Z of 0.05, 0.7 over 10. So that's the value of this Z of 0.05, 0.7 over 10. So if you compute this interval, it's actually minus 0.015 through 0.215. That's the interval we are talking about here. Okay. So the procedure is very simple. So the procedure is basically use that formula and find the confidence intervals. Probably it takes longer to write than it takes longer to write the question itself. The solution is very simple. Okay. I'll conclude today's class with this example, which is a very practical example. So this is example of practical use. So this is it's on polio vaccine, and it's in 1994. The reference of this paper is given in the book, so you can check the textbook and you can find the reference. But what it does is, at random, a group of children who received the vaccine while the other group did not, or they did not receive a vaccine, they received a placebo. That means it looks like a vaccine, but there is nothing in it. Okay? Basically, it's nothing. It's a placebo. The first group of children who received a vaccine, they are called the treated group. While the group that received, it's called the control group. Okay? So we have two groups of children. One group is treated, that means they received the vaccine. The other group, they never received a vaccine, so they thought they received a vaccine, but it's a placebo, so they are the control group. Okay, we are trying to see how effective is the vaccine. So let the PC is the true proportion of polio cases in control group. And then P of T is the true proportion of polio cases in the treated group. So T stands for treated, C stands for control. Okay, so that means we wait for some time, and after some time we see how many are there in the population where we have this PC, which is a true population. Well, first of all, we cannot see the population, so we can only see the sample. So based on the sample, we have to conclude this. So PC is suppose in the entire population, what is the population of the, so what is the proportion of the polio cases in the control group, and PT is for the entire population. So not for the sample, for the population. Well, we are trying to see the for the treated group. Okay. Now, what we do is the following. So what we want is, if we want to have an effective vaccine, we want to see if this PT is bigger than PC. So goal, a vaccine is effective if the treated proportion, so the if the sorry so if we have more polio among the proportion who are not treated, then we say the vaccine is effective. Now, this is a proportion for which we didn't have any vaccine, right? So we didn't inject any vaccine for this group. So what we expect is we should have more polio among these people. So we will have PC is bigger than PT, right? The question is this true? If not, I mean, there is no point. Okay. All right. Now here is a table. The table is provided in the book. So here is the following table: group, and here is a treated, and here is a control group. So number of children, number of polio cases, and then sample proportion. Okay. So we draw a sample. Okay. When we draw a sample, so there are there are total this many, and there are 57 polio cases, and then there are 2001, 229, 199. So the proportion is basically sample proportion is 57 over this one, which is 0.000284, and here the proportion is 0.000706. Okay. So far we have for this particular sample, so this sample proportion we called it say P T hat, and this we call PC hat. So we see that PC hat is bigger than PT hat for this sample. Now this is just a sample. So will that really work? And there comes the statistical confidence interval. Okay. Now so based on this sample, a 95% confidence interval for the actual proportion for PC minus PT, difference of two proportion, can be obtained. And how do you obtain this? This is exactly what we are discussing so far. So basically, when we have the two proportions, so basically what we have to do is P of C hat minus P of T hat minus Z of alpha. So now we are talking about a 95% confidence interval. So like in the all the previous problem, in that case, we have seen that alpha in this case is 0.025, right? For the case of 95% confidence interval. And then what we have is we write this way. So it's PC hat 1 minus PC hat over whatever sample is there for PC hat. So how many samples are there? So for PC hat, there are total 201,229. So it's my N1 plus PT hat 1 minus PT hat over N2. And what is N2? N2 is this one. Okay. So this 2 PC hat minus PT hat plus Z of 0.025. Sorry, let me just write it here. Plus Z of 0.025, and then this thing. So PC hat 1 minus PC hat. Sorry about squeezing, but you get the idea. PT hat 1 minus PT hat over N2. So basically, I wrote the same thing here. Everything here is known, right? We know everything. So we know PC hat, we know PT hat, we know this quantity. So from this, I can compute this. And if you compute this, you'll get 0.00054 through 0.00087. So that's the 95% confidence interval. Now, what is important is not this particular number. So what is important is note that this with 95% confidence interval for PC minus PT, it's positive. It's not a negative number, right? So we find that with 95% confidence, PC minus PT, which is actually for the actual sample, actually for the population. So this PC, proportion of the control group, proportion of the treated group. So this is positive because we got a positive number. This interval it does not even include zero, right? So that means PC is bigger than PT. That means in the entire population, the proportion of polio patients in the control group is more than proportion of polio patients in treated group. So that means this vaccine, this particular one, is effective with 95% confidence. Okay. Now, this example was actually from the book, as I mentioned. So the exact reference is given in the book. It's from a study. It does not mean that all the vaccines will be effective, but so this is the case. Okay. All right. So that is all about it. So now we completed this entire chapter. So what we need to do for the next class, so we'll be starting the hypothesis testing. Okay. So thank you very much. If you have any questions, send me an email or stop by my office hour.